Okay, welcome everyone. It is our great pleasure to have Dan Spielman visiting us in Waterloo. It is easy and difficult to introduce Dan. Please give me a couple of minutes. Dan is currently a professor at Yale University, and he did his PhD at MIT and was a professor at MIT from 1996 to 2005. Dan has done truly original and deep research in theoretical computer science. He has revolutionized our field and initiated new research areas multiple times. I would like to give 4 examples. So in his PhD thesis, Dan designed linear time encodable and decodable rate-achieving error-correcting codes using expanded graphs. He received the ACM doctoral dissertation award for this line of work, which has inspired a lot of work on the graph-based error-correcting codes. Okay, then he worked on simplex algorithms. Simplex algorithm is known to be fast in practice but slow in theory, but no one knows how to explain that. Then, as Teng introduced the framework of smooth analysis and showed that the simplex algorithm is polynomial time as long as we slightly perturb the worst case instances. So this initiated the whole area of smooth analysis of algorithms, and this work received the Gödel Prize in 2008 and the Fulkerson Prize in 2009. And then in 2004, Dan and Teng obtained a near linear time algorithms to solve Laplacian equations, which is the topic today. This is the engine of the recent revolution of designing fast algorithms for combinatorial problems using techniques called convex optimization, beating some long-standing bounds using combinatorial techniques. This work received the Gödel Prize in 2015. Okay, and in his work of developing Laplacian solver, Dan and his collaborators have developed several new tools. An important one is spectral sparsification of graphs. So using the new techniques in spectral sparsification, combining with an original approach using interlacing polynomials, then Marcus and Resistor solved a long-standing open problem in mathematics, the Cartesian problem, which has connections to many areas. It was a major breakthrough and has generated great interest in math and computer science. Dan has received many other awards. Let me just mention one more. So in 2010, he was awarded the Navarino Prize, which is given to one recipient in 4 years, the Fields Medals in theoretical computer science. So please join me in welcoming Dan.
Thank you. So I should mention here on the slide, this is my affiliation to the Yale Institute for Network Science, which is a small institute that I run with Nicholas Christakis. I am also part of the Department of Computer Science at Yale and our new Department of Statistics and Data Science. And about 40 minutes from now, I'll explain what this figure is. So I want to tell you about Laplacian matrices of graphs and about algorithms for them. I'm going to begin by trying to give you the motivation for them, by showing you many examples in which they arise. And I will do that long before, so I'll talk about interpolation on graphs, physical models that we analyze using Laplacians. I'll tell you about problems like graph drawing, graph clustering, relations to linear programming. I'll do all that before I actually define them precisely for you. So my goal here is to motivate them. Well, I will give you things from which you can derive the definition, but I'll give you the definition. My goal is to really motivate why we are studying them. And then after that, I will tell you about some of the algorithms we have for them. So one which Laplacian mentioned is spectral sparsification. I'll tell you a little bit about that. It's one of the main tools we are using for analyzing Laplacian matrices and designing algorithms. And finally, I will tell you about solving systems of linear equations in Laplacian matrices, which, as Laplacian mentioned, Teng and I came up with some particularly fast algorithms for in 2004. I will tell you what those look like, and I will finish by telling you a very recent result by Kyng and Sachdeva, which is really the simplest algorithm for solving these that I know, which is very, very beautiful, and you will almost completely understand by the end of the talk. If not the analysis, the algorithm. You could go implement it after this. Okay, so first, let me give you an example of a problem that's related to the Laplacian matrices on graphs that I call the problem of interpolation on graphs. So I'm drawing this from a paper of Drew, Garamani, and Lafferty, although they don't describe it exactly this way. So in this problem, imagine that we have a graph like this graph, and we have the values of a function that we know at some of the nodes, and we want to guess the values of the function at the other nodes. So for example, in this graph, these nodes represent genes, and there are edges between them that come from the biogrid database when I think that, or if we think that some of these genes interact with each other. So there's experimental evidence for that. And then let's say we're trying to figure out which genes might be implicated in a disease like diabetes. And imagine that you know, due to lab experiments, something that, say, one of these genes, CDC27, is not. I don't know if you can know that, but let's pretend you do. So let's put a 0 there. And let's say that I tell you that this other gene, ANAPC10, definitely is. We'll put a 1 there. By the way, I have no idea if that's true. I just took this graph. And I put the 0s and 1s on it myself. OK, so let's assume we know that. Now we want to guess what is the probability that these other genes are related to diabetes. So if we want to guess that probability, we want to sort of fit some function to the vertices that agrees with the known values. So what Drew, Garamani, and Lafferty suggest doing is fit the function that agrees with the known values that varies as little as possible across the edges. And they measure how much it varies across the edges by they look at the sum over all edges. So always like letters like A and B to denote vertices. X of A and X of B is the value I'm fitting in the nodes. They want to minimize the sum of the squares of the differences of that across the edges. And if we do that, subject to the known values, these are the numbers we get out. So this minimizes the sum of squares across the edges. So you might think, okay, ANAPC5 is 0.3, not that likely. This one, UB2C, is 0.61. That might be the next one we decide to investigate and take a look at that one next. OK. The important thing here is this term, the sum of squares, which is the Laplacian quadratic form. And I told you could derive what the Laplacian matrix is. Whenever you have a quadratic form like this, there is always a matrix so that you can write this as X transpose LX, where L is this matrix. In this case, it's the Laplacian matrix. I will tell you what the matrix looks like later. But the important thing to get from this equation from now is that X assigns a real number at every vertex. So you can either think of that as a vector whose coordinates are indexed by vertices, or think of it as a function from the vertices to the reals. I use the two notions interchangeably. And L, the Laplacian matrix, is a matrix whose rows and columns are indexed by the vertices of the graph. Now, if you want to do this minimization, well, you know how to do that. You take the derivative, and then you solve for where the derivative is 0. And when you take the derivative, you find that what you need to do is solve a system of linear equations in the Laplacian matrix, or properly speaking, in a submatrix of the Laplacian matrix. And that is one of the main reasons I'm interested in solving linear equations in Laplacian matrices. OK, so I want to just do this more carefully again, because the Laplacian quadratic form is the central idea in this talk. Think of the Laplacian quadratic form as it takes as input a vector. The vector assigns a vertex to assigns a real number to every vertex in the graph. And the Laplacian quadratic form tells you how much that function varies across the edges by summing the squares of the differences across the edge. So the value of the Laplacian quadratic form is the sum of all of these squares. You can, of course, consider weighted graphs. If you have weights on the edges, by the way, positive edge weights. Negative edge weights is a mess. Let's only consider positive edge weights. If you have positive edge weights, you can just put a weight on the term corresponding to edge AB and take the sum, and that's a weighted Laplacian quadratic form. And you can, of course, write it in the same way. OK, I'm going to be talking a lot about Laplacian quadratic forms, so I just want to stop now and ask if there are questions. If there are questions about them that you think of later, stop me then, because I have time in the talk for questions too. So Laplacian matrices have been around for a long time. The first place that I encountered them is in understanding resistor networks in an elementary physics course. So in this case, we take our graph and we think of every edge as being a resistor. Okay, physicists do it the other way around. They take a bunch of resistors and then they think of it as a graph. But I'm a computer scientist, so I take a graph and I think of every edge as being a resistor. And then there's some natural experiments you can do. Like, I can imagine what happens if I take two of the nodes of the graph and I attach them to the terminals of a battery. So I put this one at 0 volts and that one at 12 volts. And then you can measure how much, what will the induced voltages be at every node, and how much current will flow. And physicists tell us that the voltages at every node will minimize this Laplacian quadratic form, subject to the constraints that the nodes that are attached to terminals of the battery have those voltages. So this node is going to be at 1 volt, that'll be at 0 volts, or close enough to 0 and 1 that you can't tell the difference. And then this is what the induced voltages will be. So the exact same thing that Drew, Garimani, and Lafferty were doing, but with electrical circuits, not machine learning. So maybe a less sexy application these days, but one that's still very fundamental to modeling physical systems. However, when you, by the way, I should take a look at this more carefully, because when you measure electrical circuits and electrical flow, there's actually more going on here that's worth looking at. You don't just have voltages associated with nodes. If you take a look at the Laplacian quadratic form, it's summing the squares of potential differences across the edges. But the reason it's doing that is because these potential differences tell you how much current flows. If all these resistors were resistance 1, which is the model used for the moment, then actually you're going to get 1 unit of flow going from lower potential to higher potential, or the other way around, depending on what flavor of scientist you are. You get flows on edges, so suddenly there's more meaning coming out. And you can take a look at how much flow goes in total from this node to that node. One thing we often use this to measure is something we call the effective resistance between those two nodes. So the effective resistance in between these two nodes is if you treat the entire network as one complex resistor, what is its resistance? If you remember Ohm's law, V is equal to IR, you can get a formula for that. It tells you that the effective resistance between these two nodes, if I put 1 unit of potential between them, is the reciprocal of the current flow. So one reason we like to measure this is it gives a notion of distance in graphs that has some useful properties. It used to be the way we measure distance or how similar nodes in graphs is just how far apart the nodes are. But almost all real-world graphs have very low diameter. That doesn't discriminate very much. One reason we like looking at effective resistance is, it's low if there are many short paths between two vertices, is one way to think of it. If there are many ways for the current to flow, it's low, and that tells you those two nodes are somehow very well connected within the graph, even though they might not be adjacent. Okay, so that's one physical system I like to look at. Another one of my favorites is thinking about graphs as networks of rubber bands or springs. In this case, imagine that they are ideal linear springs. So just let the edges be springs and they connect the nodes, and then the natural thing to do is to nail down the position of some of the nodes. So I could put these in those places and then let the rest settle wherever they will and see what you get. So physics tells us what we should get. Physics tells us if these are ideal linear springs. By the way, if you go to a hardware store, you can't find one. I did once go to Home Depot and bought like a few of every spring to try to find the best one for an in-class demo, and it took a while to get it. But okay. Physics tells us that the location of the nodes will minimize the potential energy, and the potential energy in a spring stretched to length L is L squared over 2. So the position that the node should wind up in should minimize the Laplacian quadratic form. Again, subject to the known constraints. So this is exactly the same thing as Drew, Garimani, and Lafferty were doing, and exactly the same thing as when you're studying resistor networks. So I want to tell you about a very cool application of this to drawing graphs due to Tut. Can I get your answer? How many of you have seen Tut's work on how to draw a graph? Okay, not a fair number, which is good, because Tut did this while he was here. Or at least he published it while he was here. And so it's one of my favorite, but not enough of you have seen it, which is a shame. Well, now you know. It's one of my absolute favorite papers. So Tut says, let's say we want to draw a graph. We do need to assume that it is planar. So there is a nice way to draw it in plane. But if you just start out with your graph, it's a jumble. You don't know how to draw it. So he says, let's pick a cycle in the graph. In this case, I found a triangle. And move it to the outside of the picture. So that it has to be a face of the planar graph. In this case, I found a triangle. nail down the position of those vertices, and now pretend that the edges are springs. And let the system settle. For those who think about such things, who want to know what this computation is doing, the first thing I implemented was just sort of like gradient descent. You know, every node to try to move towards the center of gravity of its neighbors. If you do that, actually, this computation goes on forever. You need to add in a damping term, and what you just witnessed is a second order, accelerated gradient descent method for solving the system of linear equations. Anyway, here's what we got. We got a really nice picture of this graph. And what Tut proved is if the graph is planar and three-connected, that's one caveat, this gives you a planar embedding, straight line embedding of the graph. Always. You take a face, you nail down the outside face, you let the nodes be springs, and this gives you a planar drawing of a graph. Now, it's a little annoying. As Laplacian was observing earlier, a bunch of these nodes got all put close together. There are a few ways of fixing that. In this case, I'm just going to fix it by doing the embedding from using a different face. So let's say I take this face, which was a square, if I stick that on the outside, and now let the nodes settle, this will give me a somewhat better embedding. So this is a theorem. It's amazing to me for two reasons. The first, because it's true. I mean, why should that be? Springs don't know anything about our human desire to draw a planar graph with no crossing edges. Yet they do it. The other thing that is really amazing to me about this theorem is that I proved it in 1963. Okay, if I were going to prove this theorem, I would have done 1 million examples in MATLAB before I had the confidence to go spend a year trying to figure out the proof. And I don't think Tut had those kind of resources back in 1963. It's really pretty amazing. Okay, so this is a good point to transition to one of the other things I want to tell you a teeny bit about, which is spectral graph theory. So the Laplacian matrix is one of the central objects of study in spectral graph theory. I know many of you have encountered this, but for those who haven't, the first thing to tell you, the Laplacian matrix is symmetric. I guess I didn't tell you that yet, but it is. And when you have a symmetric n by n matrix, for say n is number of vertices, then linear algebra tells you it has n real eigenvalues, I'll call them lambda 1 through lambda n, and eigenvectors, v1 through vn, that are mutually orthogonal. And it turns out that these eigenvalues and eigenvectors tell you a lot about a graph. Now, if you've had a course in spectral graph theory or algebraic graph theory, then you sort of know this. If not, what I'm going to try to do now is convince you that it should be so. I won't really tell you theorems, but I will try to convince you that these eigenvectors are telling you something interesting about the graph. At least make it sound reasonable. Now, we usually think about eigenvalues and eigenvectors, sort of this fixed point equation. The eigenvector is a vector v, so that when I multiply it by L, I get a constant times v, and that constant is the eigenvalue. More useful for most of these analyses is actually the Courant-Fischer characterization of eigenvalues, which tells you that eigenvalues and eigenvectors are solutions to optimization problems. So the Courant-Fischer theorem tells you that, for example, lambda 1, the first eigenvalue, is the minimum over all unit vectors x of the value of the Laplacian quadratic form, x transpose Ls. And that the corresponding eigenvector is the vector at which that minimum is achieved. So this theorem tells you for symmetric matrices, eigenvalues are really about minimization of something. On the other hand, for the Laplacian matrix, this doesn't get us much. And remember, the Laplacian quadratic form is the sum over edges of the difference across the edge. So for example, if x is a constant vector, well, v1 will be a constant vector, and the corresponding eigenvalue would be 0. So okay, lambda 1 for our graph is always 0. And the corresponding eigenvector is a constant vector. Okay, I'm not going to try to tell you that actually tells you much about a graph. The next eigenvector tells you something about a graph, and Courant-Fischer gives you a characterization of that. So you say, okay, let's not use the first eigenvector, let's use the next. That eigenvalue is the minimum over all unit vectors orthogonal to v1, which in this case is the all ones vector. So go over all eigenvectors, go for all vectors orthogonal to the first one, take the minimum, that gets you the second eigenvalue. And the corresponding vector is the eigenvector, which is and so on. You can characterize all the eigenvalues and eigenvectors this way. They give you the solution to optimization problems. This motivated Kenneth Hall's spectral graph drawing algorithm. So Hall wanted to draw a graph, but it might not be a planar graph, and he didn't have faces, and he couldn't nail down any vertices. So we're not going to use Cutts theorem. Instead, what we do is we take a graph this is some arbitrary picture of a graph. Let's say I give you this graph. The way he's going to draw it is by computing eigenvectors and using the eigenvectors to give me coordinates of the vertices. So in particular, remember, each eigenvector assigns a real number to every single vertex. So if I take a look at V2, it assigns a real number to every vertex. I will use that to give me the horizontal, the x coordinate for that vertex. Now I need another coordinate for every vertex. I'll use V3, the eigenvector corresponding to the third smallest eigenvector for Laplacian. That'll give me a y coordinate. That is where I have located these vertices in this picture, and I just drew the edges as straight lines. Often this gives you very nice pictures of graphs. So believe it or not, because I'm part of this Yale Institute for Network Science, occasionally someone comes into my office and says, hey Dan, I have this graph. Can you tell me something about it? Can you tell me what it is? And one of the first things I try doing is I try doing this. I try the spectral graph drawing. Usually it doesn't work. I mean, some graphs you don't get nice pictures of. But when you do, one, it's 2 lines of MATLAB code. And 3, whoever walked in your office was blown away. You give them a nice picture. Like, here's one that I like. Here is a graph. Can I get a show of hands how many of you have seen this graph? Tell me a lot about the audience. Okay, this is the airfoil graph. It comes in MATLAB. If you're a MATLAB user, just type load airfoil. It was supposedly used for modeling airflow around an airplane wing. So this is a cross-section of airplane wing, and this is a mesh. Of course, because it was a mesh designed by a human to solve a geometric problem, it has a very nice picture. This is the picture you get from the spectral graph drawing, which I would argue is still a pretty darn good picture. I mean, it's almost planar, except for a little overlap here. And really, if you zoom in on it, it's really a nice picture of this graph. This comes just straight out from taking the mesh and taking the spectral graph drawing. By the way, I've been staring at pictures like this for, oh God, maybe 25 years now, since I first walked into Teng's office, and so I'm doing this, and I have been longing for a theorem that explains anything about this. I don't know that theorem yet. But if someone can explain to me why these pictures are so nice, I would be very happy. Now, of course, not all graphs can be drawn using the first 2 eigenvectors. Some things belong in 3 dimensions. Like the dodecahedron. The dodecahedron is, properly speaking, a 3-dimensional object. And if I do it drawn in 2 dimensions, I get this, which is not, well, it's a projection of the dodecahedron. Some of you will realize the reason for this. Really, I should draw the dodecahedron in 3 dimensions. And if I did, if I took V2, V3, and V4, they would perfectly reconstruct the dodecahedron in 3 dimensions, but I can't plot in 3 dimensions. And actually, when I chose V2 and V3, I was making an arbitrary choice. So this eigenvalue has multiplicity 3. So really, to draw this picture, I chose an arbitrary basis of this 3-dimensional space to pick V2 and V3 and just projected it down. Of course, if you don't look at what your code is doing, you might not realize that. But I think for 2 dimensions, this is a pretty good picture of the dodecahedron. Here's one which is definitely bad. Now this is Erdős's co-authorship graph. So I took every paper written by Paul Erdos. I made nodes for each of the authors and put an edge between 2 of them if they had co-authored a paper with Paul Erdos. It was disconnected, so I took the I didn't put Paul Erdos in it, that would just be silly. I took the largest connected component, and this is the picture you get. Okay, it's not a great picture. It doesn't always work. But there's a reason it doesn't always work, and we can sort of understand why it doesn't work sometimes. So you can think about, what does a nice picture of a graph look like? The edges should be relatively short. If edges are all really long, you're not getting a nice picture, you're not getting much information. And the vertices should be relatively spread out. I want the edges short. I don't let you do that by putting all the vertices in. Right? They've got to use the space. And if you have a nice picture of a graph, then you can prove that lambda 2, the second eigenvalue, would be close to 0. So I actually often like to make this a graduate homework problem, which this is something I learned from Giancarlo Roda. I tell my students, state formally and prove that if you have a nice picture of a graph, then lambda 2 is close to 0. And you can do it, and I'll tell you what the proof is later. So I guess since this is going to be videotaped and put online, I can no longer use that as a homework problem. But we'll see that if lambda 2 is reasonably big, like more than like 10 over the square root of the number of vertices, then there is no nice picture. The converse is unfortunately not true. Lambda 2 can be small, and there still can be no nice picture. But at least this, when someone, look, there are a lot of times when you try to draw a graph and you don't get a good picture, and maybe your advisor says, well, just work harder and get a better picture of the graph. You can tell them, hey, let's go look at lambda 2, and if it's big, then you can't make a nice picture of it. Okay, so here's a reason why. The Laplacian matrix of a graph in lambda 2 is related to the problem of clustering in graphs. So one of the things we often want to do with graphs is identify what physicists call modules, or what I call clusters, usually small sets of nodes that are well connected to themselves but not well connected to the outside. So if we're going to look at those, one of the things we have to measure is how well connected are they outside. We look at the boundary. So those are these bold edges here. The edges, say, going between the set S and the outside. So the Laplacian lets us measure the boundary. The vector we want is the characteristic vector of the set S. So I put 1 at all of the nodes in S and 0 outside. That'll be my vector x. And if you take a look at x transpose Lx, or the Laplacian quadratic form, it is the size of the boundary. Because you're summing over every edge the square of the difference. So when you're summing over the edges in the boundary, you're taking 1 minus 0 or 0 minus 1. You get a 1 for each of those. And outside, you get 0 minus 0, that's 0. And the edges inside, you get 1 minus 1, that's 0. So the Laplacian quadratic form lets you measure the boundary of sets of nodes. And you can basically argue without too much work that if your graph has a nice picture, where the nodes are spread out, reasonably distributed, and the edges are short, then you can find a large set of nodes with a small boundary. And if you get a large set of nodes with a small boundary, well, it doesn't tell you that this is small. Well, OK, you need to normalize your vector. Remember, my vector has to be a unit vector. This was a 0, 1 vector. So actually, you need to normalize and make it orthogonal with respect to the L1's vector. So subtract off some constant of the L1 vector. And if you have a nice picture, this will give you you get a large set, small boundary. This will tell you lambda 2 is small. OK, so Laplacian quadratic form is related to boundaries of sets and clustering. We can go the other way. One of the most popular heuristics for graph partitioning and finding clusters in graphs are what we call spectral clustering heuristics. And they leverage this idea. They say, hey, if I want to find the set of small boundary, why don't I start with an eigenvector? If I can take an eigenvector of V2, the smallest non-zero eigenvector of the Laplacian, I know that the Laplacian quadratic form is small. So like I made a fake example where I put this vector. What we then do to find sets that we think might be a good partition or a good cluster is we look at level sets. So for example, here I drew S as the set of nodes, all of whose value I think was greater than 0.75. So these, we empirically find, often give us good clusters of graphs. I think that was first observed in papers of Jonathan Hoffman and later improved by Barnes and Hagen and Kyng. And this was a lot of work mainly looking at graphs in scientific computing. So here I did the reverse. Here I looked at the set of all nodes for which V2 was less than something rather than greater. Well, the complement, the other level sets, the small direction. What they're doing is they're saying, take a look at these spectral pictures and look at the set of all nodes on this side, corresponding to some vertical line. You can actually prove that this is a good approximation of the optimization problem of finding sets of nodes whose ratio of edges inside to edges on the boundary to edges inside is small. That's called Shiger's inequality. So I won't state it formally, but Shiger's inequality, it enables you to prove that this is actually a reasonably good approximation of the best partition you can get. And for the airfoil graph, this is what it gives us, the original. And it's a reasonable partition. OK, so that is most of what I want to say about motivations of the Laplacian matrix. Now I will tell you what the matrix is. By the way, I'm actually being nice. When I first learned about Laplacian matrices, I was given the definition of the matrix and told to prove all sorts of things about it. And had I only realized what the corresponding quadratic form was, that first homework would have been trivial. So really, like, thinking about the quadratic form is much easier than thinking about the entries of the matrix. Okay, so here is a graph and its corresponding Laplacian matrix. What you will observe is that for every edge in the graph, the matrix has an off-diagonal entry of -1. This is if it's unweighted. So for example, the edge between vertex 2 and 6 corresponds to -1 in row 2 and column 6, and the matrix is symmetric, so we have the same thing in row 6 and column 2. The other off-diagonal entries are 0, and an important property of this matrix is that it is diagonally dominant, or in this case, weakly diagonally dominant. In particular, the diagonals are equal to the sum of the absolute values of the off-diagonal entries in the row and column. Or in this case, the diagonals are the degrees of the nodes. So that is what the Laplacian matrix looks like. Now, if you want to prove that, it's easiest to work from the Laplacian quadratic form. If you take the Laplacian quadratic form, remember it is a sum of squared quadratic terms, one for each edge. So what that means is we can write the Laplacian as the sum of baby Laplacians, one for each edge. Like I will let LAB be the Laplacian matrix, just corresponding to edge AB. And if you look at what you want that to be, you want that to be the matrix that gives you the quadratic form x of a minus x of b squared, and that has a nice form. So for example, if I just have edge 1, 2, this is what the matrix L1, 2 looks like. And the reason actually is it's the outer product of this vector 1 minus 1 with 1 minus 1, which is exactly what you want, because if you multiply this by x, this gets you, say, x of 1 minus x of 2. And then you square it. To get the other ones, just pad with zeros appropriately. So any LAB, you just embed this in. Okay. That is how we get Laplacian matrices. And why I'm giving this talk is because of the result that she mentioned earlier. A number of years ago, Teng and I came up with a remarkably fast algorithm for solving systems of linear equations in Laplacian matrices, building on work of other people, but instead I will tell you about the work that builds on ours. So the running time of this algorithm is nearly linear. The running time looks like order n, where m is the number of edges in the graph, times some power of log n, where n is the number of vertices, times a log 1 over epsilon, where this is actually getting to an epsilon approximation, and the time is proportional to log 1 over epsilon. So that's like about as good as you want to get. You're going to get in terms of running time, in terms of the approximation quality. I'll define approximation quality precisely for you in a moment. First, I want to focus on that constant c. So this was a nearly linear time algorithm, but in our initial paper, that constant c was about 100. So that's not efficient by any stretch of the imagination. But if you take a look at our paper, which actually we later split into 3 papers to emphasize the ingredients, it really needed 2 ingredients that were particularly important. One was something called low-stretch spanning trees, and another was something called sparsifiers. And in the years after we wrote this paper, people kept improving those ingredients. And we got better and better sparsifiers and low-stretch spanning trees and better ideas about what to do with them. And this constant kept getting lower and lower and lower until it eventually got down to 1. So Kudus, Miller, and Teng wrote a really nice paper with a very simple way of doing this, where actually they got rid of the sparsifiers and replaced it with some cool random sampling. And this got a running time. Okay, there's that tilde on the big O is hiding a log n. I hope you'll excuse me for not writing that. It's ugly on the slide. But log n squared. Anyway, m times log n log 1 over epsilon. And I'll admit, I thought we were done at that point. Until Cohen, Kyng, Pachuki, Peng, and Rao got the constant c down to 1/2. Okay, so to emphasize that, that's like m root log n. If you only want to solve a system to constant accuracy, this is less time asymptotically than would be required to sort the non-zero entries in the matrix. That said, right now the constant in the big O is a little on the big side. So implementation-wise, this does not need sorting. But still, we're doing pretty well. And that's it. And that maybe supports why there's some pretty good code for these. So, like, there are variations of the algebraic multigrid that are pretty good. Kudus has some code called the combinatorial multigrid. Actually, it's based on an algorithm from this thesis, which was before that paper. Both of those solve systems and linear equations in Laplacians pretty darn quick. None of them are exactly what we can theoretically analyze, but that's okay. because when you're solving systems of linear equations, you can check if you got the right answer. So, at least, because, you check, you compute x, and then you multiply by the Laplacian, you see is it b. And if it is, you're happy. If not, you run to a different algorithm. So, okay, maybe I have a couple of things to learn. Okay, I mean, maybe I'm lying a little bit there. I'll tell you exactly why. So let me tell you what I mean by an epsilon approximate solution. So I will say that x tilde is an epsilon approximate solution to this system of equations. Well, might want to say first that if the norm of x minus x tilde, x is the true solution, I say that I want the norm of x minus x tilde to be like less than or equal to epsilon times the norm of x. And this would be completely intuitive if I were doing this in the Euclidean norm, but I'm not. We're going to measure this in the matrix norm. So that's why there's a little LG symbol there. What that means is the Euclidean norm is usually the square root of V transpose V. Here we put LG in the middle. Now, you might wonder why I'm measuring the error this way. It was not my first instinct. My first paper on this was sort of horrible because we kept trying to do it in the Euclidean norm. But all the numerical linear algebra folks were using this matrix norm. And the reason is because, one, this is the norm in which error guarantees naturally occur, say from the preconditioned conjugate gradient. But also, for almost every application I know, this is the norm in which you want to measure the error. Meaning, if you are using Laplacian solvers as a subroutine in something else, and you want to analyze what is the impact of error in the approximation, this is the way that you want to measure the error, and this is what we give you good guarantees for. For example, maybe you want to compute eigenvectors and eigenvalues of the Laplacian to do spectral graph theory. You can do that quickly using these algorithms, but you got to be measuring the error in the matrix norm in order to get the analysis right. There's only one downside to this, which is that I don't know how to check quickly if I have small error in the matrix norm. Because in order to compute this, I need to know x. And what would be the point in that? I'm trying to compute x tilde. So this is one of the interesting gap sweeping theory in practice in this right now. We have heuristic algorithms which work really well in practice, and I can tell if they have low error in the Euclidean norm. But for a lot of my applications, I know I want low error in the matrix norm. And I can't tell if I'm getting that yet unless I go to one of my theoretically sound algorithms, which are, of course, a little bit slower. So I'm more reluctant to use them. Okay, here's one of those applications that I've been spending a lot of time on recently, which is applications of Laplacian solvers in solving linear programming problems. So, a while ago, we realized that you could get faster algorithms for a bunch of, or at least a linear programming problem, which is max flow, and min cost flow, by running an interior point method, and then interior point methods. Actually, I got a show of hands for how many of you know about interior point methods? A lot. That's a good thing about this case. For those who don't know, basically what interior point methods do is they solve systems of linear equations a couple of times to solve a linear programming problem. And if you look at this as a black box, you're missing something. So basically, if you take a look at a family of optimization problems, like max flow, and you plug it into an interior point method, you get a nice family of linear equations out. And actually, every nice family of linear programs gives you a nice family of linear equations. In the case of all of these, you get things related to Laplacians. So for minimum cost flow injection, I realized this actually got you the fastest algorithm. Use fast Laplacian solvers inside an interior point method. This is that time the fastest asymptotic algorithm for min cost flow. We now have many, many more examples. So Madri has sort of souped up interior point methods to get faster algorithms. One of the surprising problems this gives you the fastest algorithm for now is shortest paths. Now, shortest paths you think of as very easy, but this is the case where you have both positive and negative edge lengths. Think arbitrage, really. But if you have positive and negative edge lengths, then it is a somewhat messy problem. This interior point method is asymptotically the fastest. Kyng and Sachdeva had an interesting paper on using this for isotropic regression, which is a classic problem in statistics. And I then worked on using that for doing what we call Lipschitz learning. Basically, it was a regularized version of the interpolation on graphs problem that I gave you before. And it turns out that the way of regularizing this, we can solve very quickly using these interior point methods. And actually, this was very important to me, because unlike max flow, for which there's a heck of a lot of code out there, there was no code other than what we wrote for this. So our choice in writing this paper was either use standard black box linear programming algorithms, or we had to write our own. And writing our own in that case was much, much faster. Let's solve this quickly. And let me tell you a little bit about what the max flow case looks like. So probably almost all of you know max flow. We remember it's this problem where you have a graph and you want to send stuff from S to T usually. And you have directed edges, you can send things along, and they have capacities, which are always right below here. So your problem is usually, and the amount of flow that comes out of S is equal to the amount of flow that goes into T. Your goal is to maximize the flow out of S, subject to, for every node other than S or T, the flow in is equal to the flow out. You don't have any loss. And every edge, you have to have a non-negative flow, so it's between 0 and the capacity on the edge. And we learned many algorithms for solving this. This is the answer on this problem. If you take a look at what interior point methods are doing, what they are doing in every iteration, they do a number of iterations, solving problems like this. The problems all look like this. They look like minimize. This is like the sum over squares of edges of the amount of flow on an edge times some weights. Subject to saying, okay, we have to fix the value of flow in and flow out, and we play around with that. Then they get this minimization, or sorry, maximization, and then no flow is lost along the way. This turns out to be exactly an electrical flow problem. And you can solve these problems exactly by using Laplacian equation solvers. And just what's different is that at every single iteration of the interior point method, the weights change. And it turns out that when the weights change, you get a whole different problem each time. But you only need to do this a few times, and this enables you to solve maximum flow quickly. And at least asymptotically, it's as fast as the best known algorithms. In practice, this is not. Where I think this is actually a win is for interior point methods from min-cost flow, where min-cost flow, the asymptotics of the algorithms are not nearly as good. And at least, okay, theoretically, algorithms of Madri are better, and the Insidford have improved this stuff a lot for min-cost flow using interior point methods. What these min-cost flow problems look like, there are a few ways to do it. Usually, you fix the amount of flow, say leaving S and going into T. And now you have a price for using every edge. And your goal is to minimize the sum over edges of how much you're sending on that times the price. So it's like a max flow problem, except you also have costs on edges to take care of. So I think we are now getting the fastest algorithms for doing it this way. So Fontolakis and Rao have been writing primal dual interior point code, and I've been supplying the linear equation solvers. This is work in progress, but it's open source. You can find it in our package on GitHub, so you can see the development as we go. And at least on a number of generators, this is giving us the fastest algorithms for big problems. Though, of course, I have to be very careful. Which algorithm is fastest really will depend on your problem. And there are a number of algorithms for these things. But here it's at least competitive, which I'm very happy about. OK, so now I can tell you a little bit about how we solve these systems of linear equations. One of the first ideas we need, I mentioned, is sparsification. So sparsification is the approximation of an arbitrary graph by a sparse graph, by which I mean one with two edges. And we can use the Laplacian to make this precise. So I will say that a graph H is an epsilon approximation of a graph G. If the value of the Laplacian quadratic forms is always close between the two graphs. In particular, I want for every vector x, the Laplacian quadratic form in H and G is between 1 plus epsilon and 1 over 1 minus epsilon. And if this holds, I'll say the Laplacians are epsilon approximations of each other, and the graphs are epsilon approximations of each other. So let's see what this tells us. And I told you that we're going to show that every graph, and we know that every graph is a sparse approximation. In particular, Laplacians measure boundaries of sets of vertices. So what this tells you that in H and G, every set of vertices has approximately the same size boundary. You might be wondering, how could that be? The reason is because when we take one graph and we approximate it by another, we get rid of a lot of the edges, but we increase the weights on the other. So you have to measure boundary by weight. And then it becomes reasonable. OK, so this tells you if one graph approximates another, every set of nodes has approximately the same size boundary when you add by weight. It also tells you that solutions to systems of linear equations are similar. If you the fact that L of H is an epsilon approximation of LG also tells you that they're inverses, or epsilon approximations of each other. But be careful, I should say pseudo-inverse, because these are singular matrices. So just look at the inverse on the range, and those are approximately the same. And it tells you things like the effective resistance between every pair of nodes in LH is in H and G are approximately the same. So there's a very strong notion of approximation, and it's reasonable to wonder why you should be able to do it and find it. Well, the first sanity check is the complete graph. Can you sparsify the complete graph? If you can't do it for the complete graph, you can't do it for anything. Well, for the complete graph, we know you can sparsify expander graphs to sparsify the complete graph. Okay, I should get a show of hands for how many of you have counted expander graphs? At least a half, that's good. I mean, computer scientists, especially theoretical computer scientists, love expander graphs. We use them to prove a zillion theorems. If you don't know about them, you can think, we call them expanders because every set of vertices has a large boundary. So there's a lot of expansion when you look at the neighborhood of a set of vertices. Formally speaking, they're graphs for which lambda 2 is about as large as possible. It's approximately 3. They often act like pseudo-random graphs, and in fact, if you take a random regular graph with high probability, that is a good expander. But we also have explicit constructions. This picture that I started my talk with, this is a complete graph on 10 nodes. This is a great sparse approximation of it. It is the famous Peterson graph. It is like what I like to think of as a small expander on 10 vertices. Okay, so I will just tell you a word about how we can compute sparse approximations of graphs. One way to get reasonable approximations is by a random sampling procedure. So what we want to do in our random sampling procedure is I want to assign a probability, PAB, to each edge AB. And then independently, I will include edge AB in the graph, probability PAB. And if I do include it, I blow up its weight. I divide by PAB. What that means is I'm including each edge in expectation with its original weight. Just usually it's 0, and sometimes it's 1 over the probability I included. This lets me measure the expected Laplacian of the graph H that I compute this way. If I want to measure the expectation of the Laplacian, I can do it term by term, and it's just the sum over all edges of the probability I include that edge, times the weight if I include it, times the Laplacian of that edge. And the probability I include it cancels the probability, the amount by which I blow it up when I do, and we get an expectation of the Laplacian. Okay, that gets you an expectation, the right matrix. It doesn't necessarily tell you anything about whether or not you're actually close and what the probability is, but it turns out that if you choose the probabilities correctly, this works very well. And there is a very natural correct choice. The probability that you include an edge is its weight times the effective resistance between its endpoints. And if you assign PAB to be the weight of the edge times the effective resistance between its endpoints, then that is actually the exact right number to use to apply the matrix Chernoff bounds, these concentration results in random matrix theory, like with Brudelson or Schmidt-Winter or Trott. If you do that, then it tells you that actually all you need is order n log n over epsilon squared edges to get an epsilon approximation of any graph. And that, if you're willing to take these results in random matrix theory as a given, that's a pretty easy analysis. You can ask if you can do better, and you can. So this is what I think is optimal, but I'm not sure. It's got to be pretty close. We know you can only do a factor of 2 better, maybe. We know that for every graph, there is a sparse approximation, that's an epsilon approximation, where the number of edges in the approximation is at most basically 4 times the number of vertices divided by epsilon squared. I can't tell you a proof of that now or how that goes, but this is within a factor of 2 of how well the Ramanujan graphs, which are the best known expanders and the best possible expanders, approximate the complete graph. And really, I guess the big question for us is should that be a factor of approximately 4? Should that be 2? We don't know yet. I'm hoping for 2. I'm an optimist, but I don't know. So right now it's a 2 plus epsilon squared. Oh, I should mention, so in my work with Batson and Srivastava, we basically proved this exists and gave a quartic time algorithm for it. Yin-Tan Li and his son just, I think this year, gave an algorithm that computes linear size sparsifiers and almost as sparse, and they do it in nearly linear time. So we can do this, at least in theory, quickly. I don't know about in practice. Okay, so then I want to end my talk by telling you about the simplest known algorithm now for solving systems of Laplacian equations. What we're going to do is we're going to speed up Gaussian elimination by random sampling. So we're going to do something I'll call approximate Gaussian elimination. This is due to Kyng and Sachdeva. So remember, Gaussian elimination takes a matrix, let's say the Laplacian, and writes it as U transpose U, where U is an upper triangular matrix. Okay, usually people use other letters. They usually say it's an LU factorization. But if it's symmetric, then they often say LL transpose. But I can't do that, because L is a Laplacian matrix. So I'll write it as U transpose U, where U is upper triangular. What we're going to do instead is compute a sparse upper triangular matrix. So the Laplacian is approximately equal to U transpose U. And that will be good enough for solving systems of linear equations. So to do that, let me remind you how Gaussian elimination works, but I'm probably going to do it a little bit differently than you learned. So let's say I want to find this upper triangular matrix U, so that U transpose U is equal to A. Here's my matrix A. One way of understanding Gaussian elimination is that it begins by finding a rank 1 matrix that agrees with the first row and column of A. So here's the first, oh, on my screen it's highlighted. It's not here. Okay, there's one color that's missing. What can you do? The idea is that this is a rank 1 matrix, and its first row and column agree with the first row and column of A. Here is the proof that it's a rank 1 matrix. I can write it as this vector times this vector transpose. Okay, that is the first thing you do in Gaussian elimination. You find that row. Then you subtract that matrix from the original. And now you have another matrix, which has zeros in the first row and column. And you keep going like this. You then find a rank 1 matrix that agrees with this matrix in the next row and column. And that, say, looks like this. And then you write this as a vector times its transpose, and you subtract that, and you keep going. And okay, that's the point where I've eliminated the second variable. When you're done, you've taken your matrix, and you've written it as a sum of outer products of vectors with themselves, where each one has more and more zeros. And you've really written your matrix as a sum of rank 1 matrices. And the bottleneck of Gaussian elimination in the running time is it's proportional to the sum of the squares of the number of non-zeros in these vectors. Because the time to subtract this is the number of non-zeros in that vector squared, because that's the matrix. Okay, so if we're going to make Gaussian elimination fast, we need to get rid of those non-zeros. Oh, right, let me finish. I forgot to say, you can take these vectors, if I assemble them together, that gives me my lower triangular times upper triangular factorization, which I can then write as U transpose U. Okay, now, what I just told you is about Gaussian elimination. I haven't told you anything special about Laplacians. Here's the special property of Laplacians that we are going to use when we do this. When you remove this rank 1 matrix from a Laplacian matrix, you get another Laplacian matrix. So this family of matrices is closed under this operation of doing elimination. And that is very important to our analysis. And not only that, we can understand what happens when we eliminate a node. So if I eliminate, say, this node, number 1 here, which corresponds to the first row and column, when I eliminate it, I add a clique on the neighbors of node 1. Because when I eliminate a node, I'm introducing new connections, I'm introducing new non-zero entries. So the idea is we don't want to add that clique. We want to sparsify it. And we want to sparsify it actually before we add it. We don't even want to write it down. We just want to find a sparse approximation and add that instead. And that is what Kyng and Sachdeva do. So when they eliminate a node, they would add a clique on its neighbors, but they sparsify the clique without constructing it. And the way they sparsify it is incredibly simple. So when you eliminate a node of degree d, there are d edges you're getting rid of. You're going to replace it by adding d random edges between these nodes. I should say they're not uniformly random. Really what it is each of these picks a neighbor, and each of them picks a neighbor with probability proportional to the weight with which it was attached to this node. Okay, that is still pretty darn simple. You can do that. And if you do that, this works. That gets you a sparse approximation. Okay, there are two technical details to make the proof work. The first technical detail is in order to prove this really works, you need that every edge has low effective resistance. The way they guarantee that is by taking every single edge and replacing it with many edges. So you can actually take every single edge and you divide it into log n parts. That blows up everything by log n. I think I wrote log squared n here. But okay, you can get away with log n. Actually, I should double check that. By the way, I'm doing 1 in my code, and that works too if you're careful. So I don't actually believe this part is necessary, but it sure helps the analysis. Okay, so there's one caveat where you blow up every edge by some number of copies, and each edge doesn't have much weight. And also you have to randomly commute the vertices before you begin. And then if you do that, everything works. And this would get you time order f log cubed n. Okay, that's not the fastest algorithm, but it is really easy to implement. With a little bit better analysis, you can get 3 down to a 2. And I believe that in real life, you can get it down here to 1. Although we don't have, that's just experiment. But again, the improvement of the analysis does sacrifice some simplicity. Here, the analysis is pretty easy. The analysis basically needs the next result from random matrix theory. So if you, Trop has a very famous paper on concentration for random matrices. And one of the things in it is about matrix martingales. He has this matrix Friedman inequality, and that's what you need. The reason I explain all of this Gaussian elimination in terms of adding rank 1 matrices together is 1, because this analysis is natural that way, but 2, that's where random matrix theory is natural. So random matrix theory likes to consider sums of random matrices. Usually when we think about Gaussian elimination, we think about applying row operations, which are products. And for that, the machinery of random matrix theory is not as natural. But if you write it as a sum of rank 1 matrices, then you can apply random matrix theory to its work. OK. So now to really finish, I'll tell you about just some recent developments. For a long time, we were wondering, what can we do other than Laplacians? There are a lot of these techniques. OK, there are a couple other families we can handle. Something called M matrices, which come up if you're solving generalized flow problems. That's where edges can be lossy and flow leaks out of them. But recently, we've got some new ones. So one of them I'm very happy about is where we have complex edge weights. So the edges have weights in the form something like e to the I theta and e to the I minus theta, which were a generalization of Laplacians. Those we can now handle in nearly linear time. We can handle one called the connection Laplacians. These come up in a lot of work in image processing. In these, you actually don't have a real number associated with every vertex. You have a vector associated with every vertex. And as opposed to your baby element, like instead of your Laplacian on one edge, your fundamental elements look like IQ, Q transpose I, where Q is an orthonormal matrix. So we can now quickly solve systems which are written as sum of those in block structure. And a very recent result of Cohen, Kellner, Peebles, Penn, Rao, and Sidford, and Vladu handles Laplacian matrices of directed graphs. So everything I was dealing with was symmetric matrices. But directed graphs come up if you want to do things like analyze random walks on directed graphs. And they enable you to quickly compute the stable distribution in nearly linear time. And there was nothing remotely fast for this node before. So that's a major breakthrough. And as I hinted earlier, I and sort of my community have been developing a lot of code for this. These days, it's in Julia in a package called Laplacians.jl. And we've been working on putting linear solves there, sparsifying. There's low stress spanning trees. Some of the interior point methods are being developed there, local graph clustering. There's a whole bunch of stuff that if you look at, I have a web page. So if you want to learn more, I have a web page called something like Laplacian's linear equations and all the other ingredients that have gone into them. And a lot of those ingredients we now have code for in Laplacians.jl. Other places to learn things, I teach classes called Gaussian Networks and Spectral Graph Theory, and I make lecture notes for them. If you look at the union of the lecture notes over the years, you can find descriptions of almost everything here. And finally, I'll mention a wonderful monograph by Nishit Fishor called LX equals B. Thank you. Pass around this mic if there are questions, but just point it out. Yeah.
I have a question regarding the drawing of the graph, the Laplacian drawing. So if we don't know anything, can we say something about classes of graphs? Like if the graph is an interval graph or a chordal graph, can you say something about
I said if the graph is chordal or?
yeah, say chordal or interval or any other class.
That's a good question. I don't remember, honestly, if you can say something about it, if it's chordal or interval, but someone else may. I'm going to look at Chris as my best hope. But okay. Oh well. Yeah, I don't know for that off the top of my head. Though those right, matrices do have a lot of nice properties associated with them, so you think that you should be able to say something, but I'm not sure.